Hello everybody, welcome to this lecture which is about numerical differentiation. I will use the book of numerical analysis by Burden and Ferris 8th edition. First of all, why it is important to study numerical differentiation. One answer to this is numerical differentiation is used in the numerical solution of ordinary differential equation and partial differential equations. And the second answer is if we have some function which is not explicitly given but its values are given and we need to find the derivative, so numerical derivative will be used in that case. For example, in this problem, if a car is traveling on a straight road, use the following times and position to predict the speed at each time listed. That is, we have to find the numerical derivative at t is equal to 0, 3, 5, 8, 10, 13. Here s of t is a function, but it is not given explicitly. So we use numerical derivative for solving such problems. Now, the derivative of a function, if at any number x is the limit h approaches to 0, f of x plus h minus f of x divided by h. This is the derivative at any x. If we put x is equal to x naught, this will be the derivative of function f at particular number x naught. Similarly, double derivative is also defined as the limit of f dash x naught plus h minus f dash of x naught. We can say that double derivative is the derivative of derivative, and so on. We can also find third, fourth, and so on. Now, numerical differentiation means we need to find an approximate formula for the derivatives. So if we have if we are given some points x0, x1, x2 up to xn along with their function values, and we want to find the numerical derivative, first derivative, second, and so on. First of all, we need to find an interpolating polynomial. So let us use the Lagrange interpolating polynomial for this purpose. And the function f of x is approximately equal to the nth degree Lagrange interpolating polynomial summation of f of x k ln k of x, where ln k of x are the Lagrange coefficients, f of x k are the values given in above table. So simply find the derivative of this Lagrange interpolating polynomial. So we will have only the derivative of Lagrange coefficients because f of xk are constants. If we put x is equal to x0 or x1 or x2 up to xn, we can find the derivative of the numerical derivative at particular xj, where j varies from 0 to n. Similarly, we can find the second derivative in the same manner. Note that this is called n plus 1 point formula for first derivative and n plus 1 point formula for second derivative. And if we find a triple dash, so that would be n plus 1 point formula for third order, and so on. Now let us try it for n is equal to 1. In this case, n plus 1 will be equal to 2. So we have 2-point formula. And the given data will be x0 and x1 along with f of x0 and f of x1 given. For this data, we can find the first Lagrange interpolating polynomial, which is f of x0 L10 of x plus f of x1 L11 of x, where L10 of x is the Lagrange coefficients and is equal to x minus x1 by x0 minus x1. Similarly, L11 of x. The derivative of this Lagrange interpolating polynomial is very easy because the derivative of x is 1 and the derivative of constant is 0. So after this derivative, just putting the value of h is x1 is equal to x naught plus h, and x1 minus x naught is equal to h, x naught minus x1 is equal to minus h. So we have f dash of x, if f dash of x is approximately equal to f of x1 minus f of x naught divided by h. We can put x is equal to x naught or x is equal to x1 in this to find the derivative of the function at x naught or x1. If we put x naught for x, this will give us the forward difference formula, and if we put x is equal to x1, this will give us backward difference formula. In order to remove the confusion of two formulas, let us use only one formula, which is f dash of x naught approximately equal to f of x naught plus h minus f of x naught divided by h. If h is positive, this would be called forward difference formula, and if h is negative, this would be a backward difference formula. So this will be further explained in the following example. Example number 1. Use the forward difference and backward difference formulas to determine each missing entry in the given table. This means that the points 0.5, 0.6, 0.7 are given, and these are the function values, and we have to find the derivative of the function at 0.5, at 0.6, and at 0.7. These are the missing entries. So to find the derivative of the function at 0.5, let us denote x naught equal to 0.5. Denote 0.5 by x naught. And 0.1 is equal to h. So use these values in the above formula. F dash of 0.5 will be f of 0.5 plus h minus f of 0.5 divided by h, putting the values of x naught and h in this formula. And this is of course forward difference formula. And the answer is 0.852. Please note that to find the derivative of the function at 0.5, we have to use forward difference formula. To find the derivative of the function at 0.6, we can use both forward difference formula and as well as backward difference formula. But for 0.7, we have to use only backward difference formula. Look at this. X naught equal to 0.6 and h is equal to 0.1. This is forward difference formula. If x naught equal to 0.6 and h is negative, now again putting the values f dash of x naught approximately equal to f dash of x naught plus h, where h is minus 0.1, minus f of x naught, which is 0.6, divided by h, which is minus 0.1. Okay, so the answer would be this 0.852. Similarly, for 0.7, sorry, x naught equal to 0.7 here, 0.6 is wrong, and h is equal to minus 0.1. So f dash of 0.7 will be equal to f of 0.7 minus f of 0.6 divided by 0.1, and this is the derivative. This is how to use forward and backward difference formulas. Now let us try n is equal to 2. For n is equal to 2, n plus 1 point formula becomes 3-point formula. And the given data will be x naught, x1, x2 along with function values f of x naught, f of x1, and f of x2. Again, the key role is of interpolating polynomial. So in this case, we have to use the second Lagrange interpolating polynomial, in which we need three Lagrange coefficients, L20, L21, and L22. Putting all the values and multiply the two terms x minus x1 and x minus x2, and similarly the two terms in uh, I mean multiply x minus x1, x minus x2 in the first term, and similarly in the other two terms, using this formula x minus a into x minus b equal to x square minus a plus b into x plus ab. Now it is easy to differentiate because the derivative of x square will be 2x, and the derivative of minus a plus b into x is minus a plus b. The derivative of ab is of course 0. So by doing this, we have a general 3-point approximation formula where we can use x is equal to x naught, x is equal to x1, or x is equal to x2. Also note that this formula can be used for both unequally spaced data or equally spaced data. If we use equally spaced data, we can simplify the above formula. Equally spaced data means if we have x naught, x1, and x2, so the distance between x naught and x1 is the same as the distance between x1 and x2, and so on. So x naught is of course equal to x naught, x1 equal to x naught plus h, x2 is equal to x naught plus 2h, or we can also write x1 plus h. In above formula, we will use x1 plus x2, x naught plus x2, and x naught plus x1. Also, we will need 2x1, 2x2. Now, if we put x is equal to x naught and the general 3-point formula, we have f dash of x naught now and 2x naught here. Similarly, 2x naught in the second term and 2x naught in the third term. Now use the values of 2x naught minus x1 plus x2. Let us go back. From this, x1 plus x2 is equal to 2x naught plus 3h. From here, we can say 2x naught minus x1 plus x2 is equal to minus 3h. Similarly, 2x naught minus this will be minus 2h, and 2x naught minus this will be minus h. Using these values, and also x naught minus x1 is of course minus h. Using all these information from equally spaced data and simplifying, we have derived this formula, which is called 3-point endpoint formula for first derivative. Similarly, we can put x is equal to x1 and the generalized 3-point formula, and then use the information from equally spaced data and simplify. We get another formula, which is f dash of x naught plus h approximately equal to 1 over 2h f of x naught plus 2h minus f of x naught. Note that whenever we find the derivative at some x naught, so we need to replace this x naught plus h by x naught. If we do this, so look at the picture. Also, if x naught plus h is replaced by x naught, so x naught will be replaced by x naught minus h, and x naught plus 2h will be replaced by x naught plus h. Therefore, this formula becomes now f dash of x naught approximately equal to f of x naught plus h minus f of x naught minus h divided by 2h. And this is called 3-point midpoint formula. If we put x is equal to x2 and the generalized 3-point formula, This gives the same formula as formula number 2, which was 3-point endpoint formula. The only difference would be we will have minus h instead of h, or we can say h negative. This will be explained in the example. Example number 2. Use the most accurate 3-point formula to determine each missing entry in the following table. And of course, the missing entries are f dash of 1.1, f dash of 1.2, f dash of 1.3, and 4. So we have two formulas. One is 3-point endpoint formula, the other is 3-point midpoint formula. Most accurate 3-point formula means we have to use all possible values of h. For example, this is 3-point endpoint formula. So according to the given data, as we have 1.1, 1.2, 1.3, and 4. To find the derivative of the function at 1.1, f dash of 1.1, let this is x naught is 1.1, and h is 0.1. So 3-point endpoint formula can be used for f dash of 1.1. So to put values, minus 3 f of 1.1, x naught plus h will be 1.2. Because x naught is 1.1 and h is 0.1, so we have 1.2, and x naught plus 2h will be 1.3. Similarly, look at the other point, 1.4. Note that 1.1 and 1.4 are the endpoints in this table. So of course we have to use the endpoint formula for both these cases. But in case of 1.4, we have to choose minus 0.1. Look at this, minus 3 f of x naught. If h is minus 0.1, so x naught plus h will be 1.4 minus 0.1, which is 1.3, and x naught plus 2h will be 1.2. 2h will be 2 multiplied by minus 0.1. By calculator, we will have this result, which is positive. Similarly, 3-point midpoint formula can also be applied for the given data. If we use x naught equal to 1.2 and h is equal to 0.1, so f dash of 1.2 will be f of 1.3 minus f of 1.1 divided by 2 into 0.1. And if x naught is 1.3, h is 0.1, we can also use this formula again in this case. The solution to example 2 completes here, because if we look at the table, to find the derivative of the function at 1.1 and 1.4, of course we have to use endpoint formulas. For 1.2 and 1.3, we have to use midpoint formulas, but it depends on the statement of the question. If it is asked that use the most accurate 3-point formula to determine each missing entry, so this is what we have to do. Endpoint formula for the derivative at 1.1 and 1.4. Here h will be minus 0.1 and here h will be 0.1. But to differentiate, you have to find the numerical derivative at 1.2 and 1.3. We can use both midpoint and left endpoint, but the most accurate would be the midpoint. But if we want to use all the applicable 3-point formulas, if it is asked in the question to use all the applicable 3-point formulas or all for all possible values of h, then we can also use 3-point end-point formula for 1.2 and 1.3. In case of 1.2, h will be 0.1. In case of 1.3, h will be minus 0.1. So if it is the question to use all the possible values of h, so look, we can use endpoint formula for all of these values 1.1, 1.2, 1.3, and 1.4. But midpoint formula can be used only for the derivative of f at 1.2 and 1.3. Okay, now come to the another example, example 3. Use all the applicable 3-point formulas to approximate f dash of 2.0 for the following table. Or this also means that you use all applicable 3-point formulas with all possible values of h. So look at the data. Here we only want to find the derivative at 2.0, not at all the values. So to find the derivative, numerical derivative of the function at 2 only, we can use the the endpoint 3-point formula, 3-point endpoint formula with h is equal to 0.1 and minus 1, minus 0.1. Because if x naught is 2, then x naught plus h will be 2.1 and x naught plus 2h will be 2.2 if h is 0.1. Similarly, if x naught is 2 and h is minus 0.1, so we will have x naught plus h 2 minus 0.1 will be 1.9. X naught minus 2h, sorry, x naught plus 2h, x naught minus 2 into 0.1 will be 1.8. So that's why we can use left point endpoint formula with both h.1 and h minus 0.1. Similarly, the midpoint formula is also applicable here with h is equal to 0.1 and h is equal to 0.2. Also note that the above data of example 3 were taken from f of x is equal to x e to the power x, and we know that its first derivative is x e power x plus e power x. We can find its exact value and compare with the numerical. All this was about the first derivative only. Now let us derive the formula for second derivative. Note that for second derivative we need at least n is equal to 2. That is, we need at least 3-point formula for second derivative. So in this case, the given data are x0, x1, x2 along with their function values, second degree Lagrange polynomial. As in page number 3 we have done this, and f dash is this. So let us find its second derivative. What is the derivative of 2x? That is 2, and this is constant. Similarly, in each term we have 2 and the derivative of the constant is 0. So we have 2f of x naught, 2f of x1, 2f of x2 in the numerator, and denominator is the same as in above expression. As we know that f double dash of x is the constant given on the right hand side of this formula, we can put x is equal to x naught, x1 or x2 to find the derivative at x naught, x1 or x2. But again, this is not simplified formula. We can only simplify if we use equally spaced data. The above formula can be used for uh, equally as well as unequally spaced data. But for equally spaced data, we can simplify the above formula. If we use the information from equally spaced data, so we will have x naught minus x1 as minus h minus 2h here. Similarly, h minus h here, 2h h here. Formula number 1 is the derivative, double derivative of f at any x. We have x naught, x1, x2 here. If we use uh, the information from equally spaced data, which is x1 is equal to x naught plus h and x2 is equal to x naught plus 2h. So this is the endpoint formula for second derivative. And if we put x is equal to x1, we will have another formula, and again we have to replace x naught plus h by x naught, so that x naught plus 2h will become x naught plus h and x naught will become x naught minus h. Now we have another formula, if double dash of x naught approximately equal to f of x naught minus h minus 2 times f of x naught plus f of x naught plus h by h square. This is called second derivative midpoint formula, or we can say second derivative midpoint 3-point formula. If we put x is equal to x2 in the general 3-point formula for second derivative, we will have this expression same as the uh, above number 2, but the only difference is that we have minus h instead of h. Let us solve an example on this also. Example 4. Use all the applicable 3-point formulas to approximate f double dash of 2.0 for the following table. We want to find the double derivative at 2. So x naught is 2, and this is endpoint formula. Use endpoint formula for f double dash of 2. We can use h is equal to 0.1 and minus 0.1, because if x naught is 2, x naught plus h will be 2.1 if h is 0.1, and x naught plus 2h will be 2.2. Similarly, if h is minus 0.1, x naught is 2, x naught plus h, which means that 2 minus 0.1, that will be 1.9, and x naught plus 2h with h negative 0.1 will be 1.8. So we have used endpoint formula for double derivative. And for midpoint formula of second derivative, we can use h is equal to 0.1 as well as 0.2. We can also find the true error, because the data in this example were taken from this function f of x is equal to x e power x. This is the first derivative, this is the second derivative, and this is the actual value. If we compare the approximation where h was equal to 0.1 midpoint formula, so the error of this approximation is true error is exact minus approximate, which is 0.036. So I hope you can solve these questions. I'll see you in the next lecture.